Alright, so this is our Riemann sum. The area is approximated by adding up the areas of n rectangles whose heights are given by the value of the function, the output value, and whose widths are all constant, all the same width. We call it delta x. Delta x is found by taking the total width of the interval and dividing it by the number of rectangles we are using. This formula then will help us identify the x-coordinate, that is the right endpoint of whichever subinterval, ith subinterval, that we happen to be on at the moment. Now, the function that we used initially was f of x equals x squared on the interval from 0 to 2. Now, we already went through the manual calculations of approximating the area using a single rectangle, using 2 rectangles, and using 4 rectangles. The idea is that we want to be able to use this because it's actually going to be considerably faster when we go to larger and larger and larger numbers of rectangles. That being said, we should probably start by verifying it first because, yeah, I mean, you can go back and watch the video where I developed this a dozen times, but it's some pretty intense stuff going on in there. So it'd be nice if we could actually verify that it works. So I'm going to remind you from the previous video that when we did this with 4 rectangles, we got 3.75 as our approximation of the area. Let's try this guy out and see if we get the same thing. Okay, so first off, delta x. We start there. We can't do x sub I without it, so delta x is always a good place to start. Now, the endpoints of the interval are 0 to 2. So if we want to know the total width of the interval, we take the right endpoint minus the left endpoint, which of course is 2. And we divide that by the number of rectangles we're going to use. Now, I can simplify that. I could turn it into a decimal even. That's not always actually the best idea. In fact, I'm going to suggest that leaving it as an unsimplified fraction is actually going to be a good way to go. You'll see that as we get into this later on. I'm going to leave that as an unsimplified fraction. Now, we know the value of a, that's 0, and we now know the value of delta x, 2 over 4. Well, the nice thing is then that the 0 kind of just drops out, and what we're left with is 2 over 4i. Again, I'm leaving the 2 over 4 unsimplified. It will help later on to have it in unsimplified form. Now, we have delta x. We can put that in. And we have x sub I, but x sub I itself isn't what we need. What we need is f of x sub I. So I'm going to throw one more little wrinkle in here. F of x sub I. If we do these individual pieces here, we can just put them into the summation formula as we need to. So f of x sub I means that we're going to take the formula for x sub I and use it as the input to the function. F of x said to take the input and square it.
Jesus, go upstairs now. Go upstairs right now. Hold on.
So f of x sub I is equal to 2/4 I squared, which is then 4/16 I squared. Again, I'm purposefully leaving this unsimplified for the moment. Now, we've got the pieces we need. we have a formula where all we need to know is the value of I. All we need to know is which subinterval we're on, and this will be the height of that rectangle. And this is the width. So let's put it together. The sum from 1 to 4 of 4/16 I squared times 2/4 f of x sub I times delta x. This is actually not that bad when you think about it. We can multiply the 2/4 and the 4/16 together. And what we've got now is a very simple sum to evaluate. We can bring the coefficient, the 8/64, out in front by the constant multiple rule for sums. And what we have after that is the sum of I squared, for which we have a formula. Provided, of course, that our indexing variable starts at 1, which it does. We designed the whole thing that way based on the idea that we're using the right endpoint of each subinterval. So that worked out perfectly. So we've got 8/64 times, well, the formula for I squared using n equals 4. 4 times 4 plus 1 times 2 times 4 plus 1. Actually, a neat little interesting thing is that it's always n, 1 more than that, and then this number here is actually those two added together. It's actually a quick way to go through that. So, calculators are our friend here, but we can also do some cross-simplifying. So the 4 can cross-simplify with the 64 a little bit. Actually, the 8 can at this point cross or simplify with the 16. Even the 9 can simplify with the 6 a little bit. They both divide by 3. Then what we're left with is a lot less stuff to deal with, even without a calculator. 5 times 3 is 15. And in the bottom, 2 times 2 is 4. Now, that doesn't look anything like the answer that we got originally when we did it manually. But perhaps that's because one of these is in decimal form and the other is in fraction form. If you actually divide 15 by 4, you do get 3.75. So that's pretty amazing. This procedure worked. It provided the correct answer that we got when we did it kind of manually, when we did it one rectangle at a time. Now, here's where it gets nice. Remember that we said that every time you double the number of rectangles, you get a more accurate result, but you also at least double the amount of calculations you have to do. And the more subdivisions you use, the uglier and uglier those x-coordinates that you're using for your subintervals get, and the widths get, and it just gets really, really ugly. Kind of the nice thing about this is no matter how many rectangles we use, it's never going to get much more ugly than this. Yeah, some of the numbers will get a little big, but never worse than this. In fact, let's try it out. Now, personally, I would not want to do 8 rectangles by hand. That's a lot of rectangles to find the area of. And again, the more you subdivide, the uglier the values that you have to use in your calculations are going to get. This, however, requires very little adjustment because the width of the interval is still 2 minus 0. All we have to do is change the number of rectangles we're using. Well, of course, that's going to affect x sub I, but the left end point of the interval is still 0. I is still I, so all that really changes is, again, this. Well, coming down here then, the only part of this that changes is, again, that denominator. And when we square it, well, if I may, I could square 8. Instead, I'm just going to write 8 squared. Instead of actually writing 64. Not that 64 is a problem, but can you imagine if I was doing, say, 80 rectangles? You end up with a really big denominator there. But I'm going to leave it because, remember, there was some cross simplification that went on over here. If I leave it in that form, it'll be much more manageable. So check this out. We double the number of rectangles, and all that we've done so far is change a denominator. Now, up here, we will, of course, have to change the upper limit of the sum. But beyond that, once again, all that's going to change is, so there's our 4 over 8 squared I squared, that's our f of x sub I, times delta x. This is no bigger than it was before. In fact, even now, when we multiply these together, we get in the top 4 times 2 is 8, just like it was before, because the numerators haven't changed. Now we have 8 squared times another 8, and now perhaps you can see why I left that as 8 squared. If we have 2 8s being multiplied and we multiply in a third, it becomes 8 cubed. Which, actually, is going to nicely simplify with what we've got up there. I'll leave that for a later step, though. So, isn't this great? I mean, so little has changed, really. The only things that are changing are the denominators of these fractions and the n, the upper limit of the summation. Otherwise, it's the same formula with a different value of n, of course. So we have 8 over 8 cubed, and then the formula for I squared, this time when n is 8. So we have 8 times the next value after 8 times the sum of those two numbers over 6. And again, we get cross simplification. Actually, a pretty good amount of it. We have 3 separate factors of 8 down here, 2 of which can cancel with 2 of the 8s in the top and leave us with a single factor of 8 down here. Like we saw previously, the 9 and the 6 can simplify at least a little bit, both dividing by 3. And what we're left with then is just 3 times 17 in the top. And in the bottom, the single 8 that we're left with times 2. Okay, now, admittedly, 51 over 16 is not the nicest thing, but like we saw previously, we can convert that to a fraction, to a decimal very easily. All you have to do is turn to a calculator and divide the two of them. 61 goes into 51 3 times. With 3 left over. So, again, it's shrinking. Remember that what we were looking at with this in the original region was we were looking at something that was originally a gross overestimation. And then we said, okay, let's cut down that overestimation by using two rectangles. So it's still more, the total area of the rectangles is still more than the area we actually want, but it's not as much more. And we said, well, okay, why not do that again? Again, increase the number of rectangles, and we still overestimate, but not as bad as before. Well, now we're at the point where we're using 8 rectangles, so again, still overestimating, but not as badly as we were before. So it seems that we're getting better and better and better, always just that teeny tiny bit too big. But I bet you, just going on the visual, is that if we could get this with more and more and more rectangles, we might be able to get the exact area. And as we've seen throughout this semester, it's a limit. And the first way that we've done every kind of limit was numerically. Whether it was the very first lesson of the semester, when we first introduced the concept of a limit, we started with it numerically. Then when we did derivatives, the first way we did a derivative was we looked at a table of values, and we looked at what those values were approaching. In that case, it was the average rate of change over intervals that were smaller and smaller and smaller. In this case, what we're looking at is area of a series of rectangles. And if we can use more and more and more and more and more rectangles, what we should get is better and better and better and better estimates until eventually we reach a point where we can make a conclusion about the exact area of the region. That's going to be our next video, is taking this a step further and seeing what happens when we use more and more rectangles. Let's actually do the limit.